Hello again. In this video, I'm going to show you an example calculation of the Shockley-Queisser efficiency. So here again, the model is summarized that Shockley and Queisser use. So Shockley and Queisser come from a purely thermodynamic argument. They say we have solar radiation of a black body of 6,000 Kelvin, is representing the sun, incident onto a semiconductor solar cell with a certain band gap Eg that is in equilibrium with the surroundings. So we have a cell temperature of 300 Kelvin, they assume. And then this cell is connected to an electric circuit, and the electricity is used to drive a matched load here. So the circuit is run at the maximum power point. And what Shockley and Queisser said is that in the best scenario, where we only have radiative losses due to electron and hole recombination and no other losses need to be considered, the saturation current can be calculated as the radiative flux at the temperature Tc due to the cell temperature here, multiplied with the area, multiplied with the elementary charge. So the saturation current is only given by these thermodynamic losses due to the radiation equilibrium with the surrounding in a steady state condition. And for this optimum case, then they consider also a simple diode model to calculate the fill factor from the simple diode equation here and calculate the efficiency. So let's look at the equations that you need to implement in order to do this. And I put all the equations on one slide here, so it's a slide of a lot of equations. So what needs to be done is, first of all, we of course need to know how much incident radiation we have. And the incident radiation is obtained, and here I have it in watt per meter squared, so I divide it by the area. The incident radiation is obtained by integrating the spectral irradiance multiplied with the geometric correction factor, because the sun is only covering is only at a certain solid angle and not surrounding the whole solar cell. So that means we take this, we integrate this spectral irradiance with the multiplied correction factor. That is the incident power per meter squared. The photocurrent that we obtain, also per meter squared, so the photocurrent density, is then given by the absorbed photon number, which is the integrated spectral irradiance from 0 to the wavelength of the band gap corresponding to the band gap. So only these photons are absorbed that have a wavelength smaller than the band gap wavelength. And so this energy needs to be divided by the energy of the corresponding photons. Actually, the photon energy can be plugged in as h times c over lambda. And then this integral here, that is the number of absorbed photons. And this number needs to be multiplied with q, assuming that we have unity conversion efficiency, that each photon generates one electron. So we calculate the number of absorbed photons, multiply it with q, and then we get the photocurrent for the ideal case of unity conversion from electron to photon. Also here we assume, if we do the calculation like this, that all of the energy below the band gap is absorbed in our semiconductor. So it's like a thick semiconductor where everything is absorbed. If it was a thin semiconductor where part of the photons would pass through the semiconductor, then this photocurrent would be smaller. But at the limit for optimum efficiency, we would absorb everything. Okay, so this is the photocurrent. Then we also, in order to calculate this diode model here, we also need the saturation current. The saturation current is then obtained by the spectral irradiance at the temperature of the cell divided by the photon energy, and again integrated from 0 to the band gap energy. So also here we then can plug in for the photon energy h times c over lambda. And the difference between this equation and the equation up here is that in this equation, for the saturation current, we only have the temperature of the cell. So here we use the black body spectral irradiance at 300 Kelvin, for example. While here we use the black body irradiance at the temperature of the sun, 6000 Kelvin, and multiply it with the correction factor F omega. We can actually also do this calculation by plugging in here the experimental spectrum. So instead of using F omega times L of lambda, the black body radiation spectrum at the temperature of the sun, we could also plug in here the AM 1.5 global bit spectrum, for example. Still, here we will use the thermal black body radiation of our solar cell. Okay, so then from this equation we have calculated the saturation current. Once we have calculated the saturation current, we can then calculate for different voltages U what the corresponding current I is. So we can calculate the IV characteristics. Once we have the IV characteristics, we can calculate the maximum power point. So at which voltage do we have the maximum power? And that maximum power is given by the voltage at the maximum power point multiplied by the current at the maximum power point. And then finally, the Shockley-Queisser efficiency is given by the power at the maximum power point divided by the incoming power we had up here. So this is all that has to be done in order to calculate the Shockley-Queisser efficiency. So now let's look at that in the actual code. Okay, so now we are at the Matlab code, so let's look at how I implemented it. First of all, I implemented in Matlab again, but you can implement it in Python or anything you like. And for the Matlab code, I first of all calculate what the correction factor is. So I put in what the diameter of the sun is in meters here. It's 1.39 times 10 to the 9 meters. I took the distance to the sun from the Earth, which is 1.49 times 10 to the 11 meters. And then I calculate the correction factor. Or first of all, I calculate the solid angle of the sun, omega s, given by pi times the diameter over the distance squared divided by 4. This 4 comes from this is the radius of the sun here. So diameter squared over 4, or radius squared just, it could be. And then this formula is actually also from the Shockley-Queisser paper, equation 3.3. And then the correction factor is given by the solid angle omega s of the sun divided by pi for a flat surface. And this argument you can also find in the Shockley-Queisser paper of why that is the case or how they come from there. Okay, so then we have the correction factor calculated. Then I specify for the sun a temperature of 6000 Kelvin, for the cell a temperature of 300 Kelvin. I specify a band gap of 1.12 electron volt. This I do because I want to compare it to this Marquardt paper, and they use 1.12 electron volt. And I specify a wavelength range that I will consider. So here my wavelengths lambda go from 200 nanometers to 8000 nanometers or 8 microns. So this is my wavelength range I'm going to use. And then here I'm not using the experimental L of lambda, but I'm using the black body radiation. So in order to obtain my spectra for the black body, I defined this function black body of for a wavelength range and for a given temperature. So this gives me back the L of lambda at the temperature Ts, and it gives the values. By calculating the function down here. Let me just go to the black body function. So here I defined the function black body for different wavelengths at a given temperature T. And all that it does, I define first of all the variables that are necessary, calculate the wavelength with nanometer in order to convert it to the nanometer, to the SI units in order to, if I go lambda to the 5 here, to have the correct units at the end. And so then I just calculate the spectral irradiance by the black body formula given here. So 2 times pi times h times c squared over lambda to the 5th power, and then divided by the exponential function -1 that you saw on the slides before. So this is the black body radiation. So this is the L, the spectrum of the black body. Actually, I also define here, which I will use later and which is also done in the paper, I also define here this L spectral cons for concentrated, and this is the same but with an F omega of 1. So this is without considering the geometric factor F omega. So it's only the black body radiation. And I multiply here by nanometer in order to get the spectral irradiance in terms of watt per meter squared per nanometer, as we had it before in the reference spectrum, in order to be able to compare the two later on. Okay, so next we can calculate the efficiency, and for that I also defined a function, which is this function eta SQ for efficiency Shockley-Queisser, that takes the band gap energy Eg, the wavelength vector lambda, the spectral vector L spectral black body that we calculated up here, this was the calculation, and it takes the temperature of the cell, so the 300 Kelvin. And let's go down to the function, because everything happens then in the function. Okay, black body. So here is this function eta SQ. And in this function then, what I do is I first of all calculate the black body spectrum for the solar cell at the given temperature Tc. So for example, at the temperature of 300 Kelvin for all the wavelength, different wavelengths in the wavelength vector. This might seem a bit complex. I mean, you could also calculate this already and hand it over as a vector here. I actually decided to put it in the function because then I can also hand over other spectra that are not the temperature radiation of the black body, but for example the AM 1.5 global spectrum, and the user, I don't have to worry later on about how to exactly calculate the temperature spectrum. So I just do it right here to obtain the black body radiation, again in watt per meter squared per nanometer. That's why I multiply with the nanometer here for the cell temperature. And this is assuming that the cell radiates in all directions. So therefore, I do not have any correction factors here. Okay, then we can go ahead and start all the summing for the integrals. So I have first of all here I sum all the incident power, and I called it L incident. Maybe P incident would have been better, but I called it L incident here in a sense that I take always the difference of the spectral irradiance values of the given index and the index +1. So this means no, not the difference. I take the average, so I add the two values and divide it by 2. And then I take the difference of the two wavelengths, so the wavelength interval, in order to calculate the delta L for this wavelength interval in watt per meter squared. And then this wavelength, this difference in energy or in power is then added to the total. And then I just do this for all values of lambda up to the last one, because of course I always need to have the next index as well. So this is basically integrating over the spectrum numerically. And this gives me then the total incident power here. Then I need to calculate what the number of absorbed photons is. So I need to divide the power in each wavelength interval by the energy of a single photon, and the energy of the single photon is given by h times c over lambda. And in order to convert it in electron volts, and considering that my lambda is in nanometers, I also have to divide by q times nanometer. And then I get the photon energy here in electron volt. So in the next step then, I take this delta L at the given step, divide delta L by the photon energy, and then add the new number, so number of photons in this wavelength interval, to the total number. And then in going through the for loop, this will add up all the values. Oh, and I should of course say I only add in the absorbed values if the photon energy is larger than the bandgap energy, e.g. So this is what this if does here. And as a final part of the summing, I need to sum up the black body radiation of the solar cell, so of the cell itself. And also for this, I take the average of the two adjacent values, multiply it with the interval so that I get the surface area, and I add this delta L radiation to the radiation I had before. And also here I divide by the photon energy, so in order to count the number of photons. I should also say, since all the energies here, Eg and also EII, are given in electron volts, actually I already have here an additional Q in here, and this is not really the number, but if we consider that it's already multiplied with Q due to this electron volt definition, the NRAD, so the radiative number here, is actually already a current per meter squared, and also the N absorbed is already a current per meter squared, since the energy values are in electron volt. Okay, so now I have the different integrals from the slide performed, and now I can go ahead and calculate the IV characteristics. So I define here which voltage range to consider. Then I define that the saturation current is the number of the number of radiated photons multiplied with Q. And as I argued, this is a bit misleading maybe here. The Q is already included up here, so this is already in amps per meter squared. And actually I'm doing everything in amps per meter squared, so this IS is the current density. And then the photocurrent corresponds to the N absorbed. So it's the number of absorbed photons multiplied with the charge Q, assuming that each photon is converted to one electron that flows as current. And then we have the simple model again for the IV characteristics, that the current I at a given voltage U is calculated by photocurrent minus saturation current times this exponential term here, which has the voltage in it. And I can also calculate then the power for each of the voltages by multiplying the voltage with the current, and then I'm plotting the whole thing. So let's just run the script and see what the plots look like. Okay, so now the script is running. I will just go to the first figure first of all. So here we see the first figure, and this first figure is the, I have to go back here. So this first figure that I'm plotting here is the IV characteristic for the voltage in volts and the current in amps per meter squared. And the plot looks as shown here, and we see that we get a current of around 600 amps per meter squared, and we have a voltage of a bit less than 0.9 volts in this case here. I have to put it here. So this is the plot that comes up. We have here the current, and the current is around 600 amps per meter squared. And here we have the open circuit voltage, which is a bit less than 0.9 volts in this case here. And then let's look at the power. So for this IV curve, here we can then calculate the power. And the power is then just given by multiplying the voltage with the current for each of the values, and we can see that the maximum power point is up here and gives about 450 or 480 maybe watts per meter squared at the maximum power point. So we can see from these graphics then that this is the maximum power point. So we now know that this value here is the value that we need to plug into the eta to calculate the efficiency of the device. Okay, so after plotting all of this, we can then I calculated the maximum power point. I just show you this. So the calculation of the maximum power point I do by first of all defining a function with one variable u, and this is just the negative of the power. So I multiply minus u with the current here, and then I do an fmin search to find the minimum of this negative of the power. So if our actual graph is going up, then the negative is going to go down. So we can find the minimum, and this result is the voltage at the maximum power point and the negative of the maximum power. And so I can then calculate the power at the maximum power point by again inverting it. So another minus sign here. And this I added to the plot also as a marker. And then, of course, the final value is the efficiency here. So to get the efficiency, we multiply 100 times the power at the maximum power point divided by the incident power, which I called a bit confusing here, L incident in my program. And the values that we achieve, you can see down here. So the values are for the black body radiation at a band gap of 1.12 volts, we get a maximum Shockley-Queisser efficiency of 30.3%. So 30.3% is the maximum. As I said, I also calculated for a factor f, so this geometrical correction factor as 1 for comparison. And for this geometrical correction factor, we actually get 40.9 out of this same calculation here. So I run the whole program again, but without the geometrical correction factor. So this is this second part here. I just defined here the spectrum without the geometrical correction factor, meaning that the f omega is equal to 1. And then I calculate for this case, which is called the concentrated case, and why we will see later. And here I obtain then that if f is equal to 1, then Shockley and Queisser predict 40.9% efficiency. If f is the regular value that we have for our sun at irradiant onto our planar solar cell, then we get a maximum efficiency of 30.3%. Okay, so coming back to the slides, we had all of these equations. I just showed you how I implemented them in Matlab. And then from these equations, I calculated the IV characteristics for the f omega of 2.18 times 10 to the minus 5 as correction factor. And I calculated the power for the different voltages and the maximum power point. And I obtained then for this solar cell that the incident power, which I called L incident, not P incident in my program, is 1590 watt per meter squared. And the Shockley-Queisser efficiency is 30% for this scenario. So therefore, Shockley and Queisser obtain that only considering this thermodynamic consideration and a band gap of 1.12, which corresponds to silicon approximately, we get 30% efficiency. And in order to check your calculations some more, you can go to the original figure 5 in the Shockley and Queisser paper. And what they do there is they calculate the efficiency as a function of the band gap for different values of f. And I did this as well. And I also added in here the Trivich-Flinn efficiency for black body radiation with 6000 Kelvin as comparison. And so this is kind of the big comparison graph of everything. So what we see here then is that we first of all, for the concentration factor for maximum concentration, or this geometrical factor of 1, so if we assume that, we get around 40% efficiency, which I just showed you as well. And then this is actually close to the maximum efficiency we can get. The efficiency gets lower to lower band gaps, and it gets also lower to higher band gaps. And this is again due to the argument that if the band gap is too low, we have a lot of thermalization losses. If the band gap is too high, lots of photons pass through the solar cell. What is interesting now is in considering this graphic is that what influence the factor F has on the results. So if we change this geometrical factor, or this correction factor F, then we can see that for a lower F, so the extreme is here 1 × 10⁻12, so for a lower F, the optimum band gap shifts somewhat to larger band gap values. And we can also see that the efficiency is dropping significantly. So if we think of 1955, when the saturation current that was experimentally achieved was still quite a bit less than what is quite a bit more than what is maximum possible. Therefore, then the efficiency is less, and we get one of these curves here, depending on what the saturation current is. So if the saturation current is at the optimum, then we would get, as I just showed you, the 30% efficiency. So we can see that increasing the F factor would improve the efficiency. What is also interesting is what we see, that if we look at this scenario of the max, if F equals 1, which is also called maximum concentration, it actually approaches the Trivich and Flinn efficiency. And this can be understood by the effect that if the saturation current is getting lower, that means that we get a more square IV shape. And for the Trivich and Flinn efficiency, we just assume that it's ideally square, and we can just multiply the short circuit current with the open circuit voltage and have a fill factor of 100%. And actually, so we can see here, if the F is getting closer to 1, this also means that we are getting closer to the ideal of a square situation. Of course, we can also compare the results, or we can do the Shockley and Queisser calculation with the AM 1.5 global spectrum to compare it to earlier results. And this is what I've summarized in this graphic here. So here you can see, first of all, the Trivich and Flinn efficiency at air mass 1.5 global radiation, the reference spectrum, and the Trivich and Flinn efficiency at 600 Kelvin, black body radiation. These are these two blue curves here. So you can see that if you change the radiation, it also changes somewhat what the efficiency at the maximum is. And this is due to the fact that in the real spectrum we have on the Earth, we have parts of the spectrum are taken out due to absorption, and therefore the efficiency is a bit better at the lower band gaps than it is for the black body radiation, while the black body radiation has a better efficiency for the larger band gaps. Okay, so then here I plot also the Shockley and Queisser result for the AM 1.5 global spectrum. So this I do by running my Matlab code, but instead of handing over the black body radiation, I hand over the AM 1.5 global radiation, and I get this red solid curve here. And again, in comparison to this dashed red curve for the black body radiation at 1 sun for 6000 Kelvin. And also here you can see small differences between the two. And finally, I added into this graph here the concentrated Shockley and Queisser limit for a black body radius of 600 Kelvin, 6000 Kelvin. So this means again this magenta colored curve here is for a factor F of 1, while this here is considering the correction factor due to the sun covering only a certain solid angle. So from these values, we can then see that we now, if we use the AM 1.5 global spectrum for the Shockley-Queisser limit, we actually have around 33% efficiency here for band gaps that are in the range of 1.1 to 1.3 electron volts about. So the maximum efficiency from the Shockley-Queisser limit that a single band gap solar cell can have at 1 sun illumination at a temperature of the solar cell of 300 Kelvin is around 33%. That was what was predicted by Shockley and Queisser. Well, not quite, they predicted the black body radiation, but what follows from this argument. And this is actually the fundamental limit, and we didn't include any other loss mechanisms. So that shows you that, yeah, it would be great to build a silicon solar cell with higher power, but we are already, this here is the radiation limit, so to get higher than that will be difficult or impossible. So finally, let's compare the results with what has been achieved. And this graph here I took from the Marquardt paper cited down here. So here we see again the efficiency for 1 sun illumination, first of all for the AM 1.5 global and also in dashed for the black body radiation. And we see here different types of solar cells and what efficiency has been achieved. And for crystalline silicon, the efficiency that has been achieved is here around 27%. For gallium arsenide, it is a bit higher. And then other materials, for example, indium phosphide, cadmium telluride, perovskite solar cells, they are all a bit lower than the values for gallium arsenide and silicon. Also, new approaches that are coming up, like organic solar cells, also have lower efficiency. As you can see here, but that might still increase. That's still part of research. So therefore, you can see here that, of course, none of the actual materials has an efficiency better than the Shockley and Queisser efficiency. And by using the Shockley and Queisser argument, you can check how close are you to the ultimate thermodynamic efficiency limit. Thanks for watching.